one we're working with a bromide. It's an aluminum bromide, which will actually come out a little bit later. And we're working with triethyl phosphite. And for the first step, I'm just going to write them as ET because I don't need them. The first step is just an SN2 reaction of this lone pair pushing the bromide out to create a carbon-phosphorus bond.
Max just put in the chat that you're still muted.
What's that?
Max just put in the chat that you're still muted.
Well, how about that? Sorry, Max. Didn't realize I was muted because I was looking at the QuickTime instead of the video, instead of the. There. So, we're starting with an aluminum bromide, which means the SN2 reaction is enhanced by participation of this pi bond in the transition state, and the lone pair on phosphorus is going to do an SN2 displacement. So we've got a new phosphorus carbon bond. And now I am going to show two hydrogens. Because the next step is for the bromide to just get pushed off as a leaving group to do a second SN2 reaction. Create the phosphorus oxygen double bond of the phosphidine. So we now have diethyl phosphidine. Those two steps are the Arbusov reaction. Both SN2 reactions, both good ones. This hydrogen is now fairly acidic. It's next to a phosphorus oxygen double bond, which means we can put the negative charge out on phosphorus or on oxygen, which is an electronegative element. And it's also next to a pi bond, which means that it can resonate and put the negative charge out there. So it's both a Lily and an enolizable hydrogen, since this looks very much like an enolate. So we're going to take that off, and we can do that with the relatively mild base, sodium methoxide. And let's push it onto the phosphorus, or the oxygen attached to the phosphorus, because that's going to be the most stable of the resonance structures. So that creates that phosphorane analog just by fluidity protonation. That's the nucleophile that's going to attack the formaldehyde in the first step. So we're going to reform the phosphorus oxygen double bond, migrate that carbon-phosphorus bond over to the oxygen, and you could have shown it with a lone pair here, and the phosphorus oxygen double bond already present. That would have been equally legitimate. Both of those will result in the same product that they're both acceptable. That makes the new carbon-carbon bond. Puts a negative charge on oxygen, which is close to that phosphorus. In the chat I need to know about. So now we're going to close up the four membrane. That's our nucleophilic acyl addition step, step 4. Now we're going to close up the ring. That's the equilibrium. Now have a pentacoordinate phosphorus, right? So it's got a trivial bitermite arrangement around it. And then in the last step, so this is ring closure. That's step 5. And then the last step is going to be for this pair of electrons to come back in. Push the pair of electrons from carbon phosphorus to make the new pi bond, and push this pair of electrons out onto the oxygen. And ring rearranges to get up the final product. Sodium atom that's been sitting and watching ever since it came along with the epoxide ion comes out. So 2 steps for the Arbusov reaction, and then this one, since it involves a phosphonate, is the Horner-Emmons modification. So similar, but not identical to the Wittig reaction. The advantages of the Horner-Emmons modification that I hope you pointed out in step 3 are better atom economy, because the triethylphosphide has a considerably lower molecular weight than triphosphine. A easier separation because of a water soluble product. And though it's not relevant in this case because we have no stereochemistry on the double bond, this is an E-selective reaction, and usually pretty good selectivity. So if you want the E isomer, in cases where there is an E isomer, then the Horner-Emmons modification is a good way to go. The advantages of the Wittig reaction, which is the other pathway, are it's Z selective. So if you want a Z isomer, the Wittig reaction is the way to go. It's often not very Z selective, but it is Z selective, right? So it's kind of like doing a free radical hallucination. If you want the more substituted, you choose bromine, which is good selectivity. If you want the less substituted, you choose chlorine. It's crap selectivity, but at least it's the right selectivity. So by determining whether you want the E isomer or the Z isomer, you can choose which of these phosphorus pathways you want. The other reaction effectively just does the opposite, right? Instead of having the carbonyl group on the CH2 and the bromide on the ring, it has the carbonyl group on the ring and iodide in this case on the single carbon. And by the way, this problem was basically problem 17-14, the exercise within the chapter, except that that one didn't involve the Horner-Emmons. So the mechanism is pretty similar. I didn't ask for it, but it doesn't take much to show it, right? There's an SN2 reaction here to generate phosphonium salt. This can now be deprotonated, and that was the reagent you needed that I didn't give you. That's the lithium. Take that hydrogen off to generate helium. Which that intermediate, you don't have to necessarily show the resonance structure with the phosphorus carbon double bond, which is the phosphorate. The next thing is that it's going to attack the carbonyl carbon. And you're contemplating against the product. Just like that. We're going to close the ring. This is the major key. That ring is going to break down with one bond going to form the phosphorus oxygen double bond, and the other bond going to form the carbon-carbon double bond with carbon monoxide, and same product. Like you're all set. Z-selective reaction, but poor atom economy because triphenylphosphine is such high molecular weight, and a product that has very similar solubility properties to your product that you're after, which makes it hard to get away unless, right, this is insoluble in your solvent and this is more soluble, so you can remove it just by solubility problem. But since triphenylphosphine oxide and your product are soluble in many of the same things, that strategy doesn't really work.
Does it matter in the ring opening step which arrow goes which way?
Not in most cases.
Okay.
The reason I showed it the way I did show it in this case is because that's a primary carbon, so it won't be very good at stabilizing partial positive charge. So taking the electrons from here builds up a slight partial positive on this carbon in the transition state, and that makes more sense than building up a slight positive charge on this carbon. So it's not critical, but when there's a choice, I usually take the electrons away from the more substituted carbon.
Okay.
It does matter on the other reaction, because you want to take the pair of electrons onto the oxygen to make the O- in the salt. Right, so you have to show it the way I showed it for the Horner-Emmons.
Okay.
So I'm going to stop and save this video because the last videos gave me